In a quiet room of the National Museum in Baghdad, there once sat a small clay jar that should not have existed. It was not large, it was not ornate, it did not bear the marks of imperial power or royal decree. But inside that humble vessel was a configuration of metal and ceramic that, if interpreted correctly, suggests that 2,000 years ago, someone in the ancient Near East may have stumbled onto electricity. This is the story of what many now call the Baghdad Battery, a simple clay jar containing a copper cylinder and an iron rod, capable of generating an electric charge using nothing more than an acidic liquid such as vinegar or fermented wine. If this interpretation is correct, then ancient Persia may have been experimenting with electrochemistry long before the word electricity was ever spoken. In 1936, during excavations at Khujut Rabu near Baghdad, German archaeologist Wilhelm Koenig uncovered a curious object. The jar dated to the Parthian period, roughly between 250 BCE and 250 CE, a time when the Parthian Empire controlled vast territories across Persia and Mesopotamia. Inside the clay vessel was a rolled sheet of copper forming a cylinder. Suspended in the center of that copper tube was an iron rod. The top had been sealed with bitumen, a natural asphalt substance used extensively in ancient construction and waterproofing. The configuration was simple but strangely familiar. Copper, iron, an insulating container, a sealed top. When modern researchers replicated the device and filled it with vinegar, grape juice, or other acidic solutions, it produced a small electric potential, usually between 0.5 and 1 volt. That is not enough to power a city, but it is more than enough to prove a principle. Two dissimilar metals immersed in an electrolyte create a galvanic reaction. In other words, it was a battery. Electricity does not require turbines or silicon chips. It requires a difference. When two different metals are placed in an acidic solution, a chemical reaction occurs. Electrons begin to move from one metal to the other through an external circuit. That movement of electrons is electrical current. In this case, iron would serve as the anode. Copper would serve as the cathode. The acidic liquid, vinegar, fermented wine, or even lemon juice, would act as the electrolyte. The reaction is simple. Iron oxidizes, electrons flow, current is generated. It is not sophisticated by modern standards. It does not require rare earth elements or industrial refinement. It requires metals that were readily available in antiquity and an acidic fluid that any agrarian civilization could produce. The Parthians were skilled metal workers. They produced fine jewelry, weaponry, and intricate ornamental designs. They understood metallurgy deeply, even if they did not describe it in the language of electrochemistry. The question is not whether the jar could produce electricity. It can. The question is whether that electricity was used intentionally. Some researchers believe the device may have been used for electroplating. Electroplating is the process of depositing a thin layer of one metal onto another, using electrical current. If you submerge a silver object in a gold solution and apply current, gold ions bond to the silver surface. The result is a thin, uniform gold coating. Interestingly, Parthian artifacts include finely gold-plated objects that appear surprisingly even and consistent. While traditional fire gilding methods existed, electroplating would offer more control and less mercury exposure. Experiments conducted in the 1970s by German scientist Arne Eggebrecht demonstrated that a replica of the jar could successfully plate a small silver statue with gold in just a few hours. The voltage was small, but sufficient. It is entirely possible that artisans discovered this effect accidentally. Perhaps a metal rod left in acidic liquid connected to another metal object produced a strange metallic bloom. Perhaps curiosity drove experimentation. Ancient innovation often begins not with theory, but with observation. The claim that this device generated light is more speculative but still worth examining. A single jar produces less than 1 volt. However, batteries can be connected in series. If multiple jars were wired together, the voltage would increase. With sufficient voltage, it is possible to create a spark. It is possible to heat fine metal wire until it glows faintly. Would that produce usable illumination? Not in the sense of a modern bulb. But ancient lighting did not require industrial brightness. Even a faint glow in ritual contexts might have appeared mysterious or divine. Some researchers have proposed that the batteries could have powered arc lighting in temple environments, particularly if hidden from view. Others argue that this stretches plausibility beyond available evidence. There are no surviving wires. There are no preserved lamp sockets. There are no written records explicitly describing electric light. And that silence is important. Not every archaeologist agrees that the jar was a battery. Some argue that it may have been a simple storage vessel. Others suggest it was used to preserve scrolls or sacred texts. The copper cylinder may have served as a container rather than an electrode. Critics point out that there are no direct references to electricity in Parthian texts. There is no depiction of wiring systems. There are no clear electroplated workshops definitively tied to battery use. Archaeology operates on evidence, not imagination. However, absence of documentation does not prove absence of experimentation. Many ancient technologies were discovered empirically without theoretical frameworks. The Romans built massive water mills without understanding fluid dynamics equations. Blacksmiths manipulated carbon and steel without atomic theory. Innovation often precedes explanation. To understand whether this device fits its era, we must understand Persian scientific culture. The Parthian world sat at a crossroads of Greek, Mesopotamian, and Indian knowledge systems. It inherited Babylonian astronomical precision. It interacted with Hellenistic engineering. It preserved metallurgical traditions, stretching back millennia. Later Persian scholars under the Sasanian and Islamic Golden Age would produce groundbreaking work in chemistry, optics, mathematics, and medicine. The intellectual lineage was already forming. The region was not technologically naive. If someone observed that combining metals in acidic liquids produced strange effects, it is entirely plausible that artisans would experiment further. Curiosity is not a modern invention. Whether the Baghdad Battery was used intentionally for electrochemistry or not, it reveals something profound. Ancient civilizations were capable of experimentation far beyond what we typically credit them for. They were not static. They were not intellectually primitive. They were working within their material constraints, but they were observant. If the device represented a nascent understanding of electricity, why did the knowledge not proliferate? History is not a straight line of progress. It is a fragile chain. Knowledge can disappear with political collapse. Workshops can be destroyed. Guild secrets can die with masters. Empires fall. Trade routes shift. Libraries burn. If a handful of artisans knew how to plate metal using primitive batteries, and that knowledge was not widely institutionalized, it could vanish within a generation. The fall of the Parthian Empire in 224 CE, replaced by the Sasanian dynasty, reshaped the region. Cultural transitions often erase marginal technologies. What survives is what becomes indispensable. Modern experiments have consistently shown that the jar can function as a battery. With vinegar, with grape juice, with copper sulfate solutions, it produces measurable current. That fact alone reshapes our imagination. Electricity was not discovered in the 18th century. It was described scientifically then. But electrostatic phenomena were known in ancient Greece. Magnetism was observed in lodestones in China. Static shocks were familiar experiences across cultures. The Baghdad Battery suggests that electrochemical current may have been explored as well. Even if the device was not used to generate light, the principle stands. 2,000 years ago, someone assembled a working galvanic cell using basic materials: clay, copper, iron, vinegar. That is not myth, that is chemistry. There is a tendency to view modern technology as inevitable. We assume that our ancestors were waiting for us to arrive and complete the puzzle. But history shows cycles of discovery, loss, rediscovery. The Parthian jar forces us to confront the possibility that knowledge is often fragmented, rediscovered under new names, and credited to different eras. It reminds us that innovation is not always linear, and that brilliance can emerge anywhere materials and curiosity intersect. A clay jar buried in Mesopotamian soil does not prove that ancient Persia had electric streetlights. It does not rewrite the Industrial Revolution. But it does demonstrate that the foundations of electrochemistry were physically possible long before modern theory. Sometimes the most powerful technologies begin not with a blueprint, but with a question. What happens if we place these metals together? What happens if we add acid? What happens if we connect them? 2,000 years ago, someone asked that question, and in a small clay jar sealed with bitumen, electrons began to move. If you enjoyed this video, don't forget to like and subscribe so we can keep improving the channel. See you next time.